There we go.
And Jim, Brown could always host us again, and then we wouldn't have to have a session.
That's true. So we're full screen now?
Yes, you're good to go.
Okay, great.
So we're going to mute on this.
Yeah, we'd love to do that sometime, really. We had a really wonderful time when you all were here before, and I apologize for not being there in person. I'd love to be there. Unfortunately, I'm out here on Cape Cod at the moment, so it's a terrible place compared to Denver, of course, and the area there. But we're doing okay, and I just want to, I'd like to point out today that something about impact basins, okay? That's been a hobby of mine for quite a while, since I was a little boy. And the key here is that the question is, what's going on with the impact basins in the early history of Mars? And so one of the things we've tried to do here is really kind of look at the key geological elements in deciphering the early climate history of Mars. I was 20 years ago, I came home from work, and I had a really great creative morning, and I came home and I said to my wife, I've got this ternary diagram. I think I've got the three factors in the early evolution of Mars climate, and I think I figured it out, how they relate to each other. And I said, what do you think? And, I got this triangle here. She says, looks at me straight in the eye and says, looks like a pyramid scheme to me. And she was totally right. It's like, and so the key was that, in fact, I was trying to do a forward model from an area we knew little about. And so what we did was, over the last 20 years, we've been working very hard on an inverse model. We know what's going on right now. Let's work our way back in time until we can get to the early history of Mars and say something more informed about what's going on. So that's where we are today. And of course, it gets back to the basin formation history. So if we take a look here, using these different approaches here, we've tried to look at the water, the global hydrological system and cycle. Is it globally vertically integrated or horizontally stratified? Fundamental differences, fluvial lacustrine features, marine morphology, et cetera, erosion and degradation features, really critical in terms of the magnitude and amplitude of the processes, and of course, the alteration mineralogy. What's up with all the phyllosilicates in the early history of Mars? And we use a geological process approach and a stratigraphic approach. And we've also incorporated climate modeling approaches as well, working with our colleagues, for example, Robin Wordsworth at Harvard and the people at LMD, Francois Forget and colleagues for decades, okay? So we want to get back to this period of time in early history. This is a paper, a slide from a paper that Caleb and I did some time ago. And what we're looking at here is, essentially the early history, the pre-Noachian, the Noachian, and the Hesperian, moving on into the Amazonian. So we really want to get back to where the effect of these basins are. Is basin formation. They're really dominant here. We can really tell the Hellas, Isidis, and Argyre. And of course, we have the Borealis Basin back here. And how does this relate to all these other features here? And how do we fit them together, okay? So as I said, we're starting in an inverse model, and we're starting with the Amazonian and working our way back in time. So let me try to briefly take you through there and then talk about the big basin effects in the middle to late Noachian, early to middle Noachian. We know in the Amazonian that the climate is extremely cold and arid, and it has been for quite a while. We know in the Hesperian that it was transitional, and the prevailing model now is that, of course, that it's warm and wet there. There's precipitation, warm rain, forms of phyllosilicates, does the erosion of the valley networks, et cetera. And what else do you need to know, okay? But we've really been skeptical about that for a variety of reasons, not the least of which is the faint young sun and the lack of greenhouse gases at that time. So we've looked at the hydrological system. Today, on the right in the Amazonian, we know it's it's horizontally stratified. There's a cryosphere measured in kilometer thickness that inhibits any kind of interaction between the surface and the subsurface. And indeed, the fact that the surface is so cold, you don't get rainfall there either. On the other hand, back in the early, in the Noachian, it's thought that it's vertically integrated. That is, you get rainfall on the surface, it soaks into the water table. The water table is often connected to lowlands to produce oceans and lakes and other kinds of things like that. So let's take a look at these three periods and work our way back to the pay dirt here, which is what's going on in the Noachian. We summarize the Amazonian. We know that it was a cold and hyper-arid climate throughout 2/3 of the history. Remember how long the Amazonia, 2/3 of the history, it's horizontally stratified and thick. The climate change is related to spin axis orbital perturbations. We know now that the current obliquity is maybe anomalous. Typical obliquity was likely to be more like 45 degrees, and it's definitely a horizontally stratified hydrological system through 2/3 of the history. So what about the Hesperian? This is where we know we have a lot of outflow channels here. And many people think they're fed into oceans, standing bodies of water that were then vertically integrated with the rest of the system so that you had rainfall in the highlands soaking into the groundwater, feeding oceans, fed by the outflow channels, et cetera, et cetera. We've not found a lot of really fundamental support for this. There's an excellent series of papers by Scholes and colleagues which looked at all the shorelines that have been mapped, both for the Hesperian and the late Noachian proposed oceans, excuse me, and found them, I would say, wanting in terms of real support. We support that. We've looked at all the evidence in this paper, Ahead at All 2025, that's in review in astrobiology. If you get it, please be kind. Okay, we can revise it. But that one, we found little evidence for long-term oceans. And we also did some modeling. What happens when the outflow channels empty into the northern lowlands? We find out from work that Mr. Kreslowski and I did years ago, that in fact, it's the temperatures then are highly likely to be mean annual temperature below 273 K during this period of time. And indeed, what happens is the ocean freezes over very short periods of time geologically. And indeed, you get freezing and sublimation, and it goes to the cold traps, the poles, okay? And so even if you have an ocean, it's very hard to maintain it, okay? You could get outflow channels all coming out at the same time. They actually don't all come out at the same time. That's another issue here. What happens is really that this water doesn't stay around. It goes to the poles. And really critical issues for both oceans is, where did the water come from and where did it go? We have to account for up to 500 meters global equivalent layer of water to fill these oceans. And there's just not a lot of evidence for where it came from, and most importantly, where it went. The polar caps are way short of that, okay? So these are some of the things we've talked about and thought about. And it turns out our conclusion is here that in the Hesperian, the global hydrological system is indeed horizontally stratified. It's thinner than the last 2/3 of Martian history because of the geothermal gradient being higher back at that time. But indeed, it's horizontally stratified. Occasionally, you get dikes and other intrusions to crack the cryosphere and cause the outflow channels to form, but even those are generally transient. So for the Hesperian, we conclude that the outflow channels, indeed, the long-term Hesperian oceans are unlikely. The hydrological cycle is still horizontally stratified. Well, this brings us back to the Noachian, okay? And, hey, come on, it's warm and wet, right? Valley networks, open and closed basin lakes, possibly a late Noachian ocean. We've kind of dismissed the possibility of a late Noachian ocean, but let me share with you why we think that, okay? Let's take a look at the valley networks, back to this paradigm here, which is early, middle to late Noachian. Caleb Fassett, as part of his PhD thesis, did buffered crater counting and showed that the vast majority of valley networks cluster, quite distinctly cluster right around essentially the late Noachian, early Hesperian boundary. It also shows that indeed they're not related to the Hellas, Isidis, and Argyre. And also, when you look down here at the alteration processes, they're really removed from the phyllosilicates. And the valley networks don't seem to be really closely related to anything that can produce either one of those things. And we also have the high degradation rates down here, which decrease dramatically into this period of time here. So, mystery, what's going on? So what we summarized here in the late Noachian vertically integrated hydrological system and cycle, is it vertically integrated? Is it robust? We analyzed the evidence for the nature of all these elements and found little support for a robust or interconnected hydrological system. Rainfall precipitation rates are predicted to be very low. Fluvial systems are immature. They don't really reach, Ariel Deutsch showed, they don't usually reach the northern lowlands. So they're not emptying into the northern lowlands to create an ocean. So that's not connected. The fluvial runoff events, this is really an amazing study by Stuckey and others. They looked at coupled open basin lake, closed basin lake um, features. So the open basin lake, the water flows into it, flows out of it, and then you follow that to a closed basin lake. And closed basin lake, the water, it's like the Hotel of California of lakes that checks in, but it doesn't check out. And what that does, it put constraints on the total amount of water that could be there and the amount of time it would take to do the erosion, et cetera. And they found that this was very low water volumes and they're dominantly episodic events, short term, 10 to the 2 to 10 to the 5th years. That's nothing over the course of, the several hundred million years we're talking about here. So we think that these events are likely to be caused by transient surface events and conditions rather than a continuous, robust source to sink cycle. And when we put all this together, this is a picture of Mars. There's the Hellas Basin there. You can see the white areas here are what are predicted to be the snow and ice accumulation in a essentially equilibrium line altitude here of about +1 kilometers in an early Noachian environment. Because if the atmospheric pressure was above a few tens to hundreds of millibars, any water ice in the northern lowlands would in fact sublimate and go to the southern uplands and snow out here. So you have the water where you want it in the golden icy scenario. And if you did a transient event, like is described in the cyclic way, et cetera, you could top down melt this. And this is where you'll see in green and red, all the open and closed basin lakes are. They're really clustered around here. So this argues to us that these events in the valley network systems, not only are they right at the Noachian Hesperian boundary, but they're also related to short-term transient events, very likely related to top-down melting of snow and ice. So we would conclude from this then that even back into the Noachian, okay, the hydrological system was not vertically integrated, but was horizontally stratified. We already have really good evidence for that over the course of a significant percentage of the, 80% of the surface, 80% of the history of Mars. And we think that that's likely to have been the case back then. So wait, what's going on here? Warm and wet, arid, robust, vertically integrated hydrological system. We don't think we see a lot of evidence for either of those. Basically, the valley networks are separated in time into the late Noachian, early Hesperian, clustered around here from transient events, et cetera. And this raises the question, and what's going on with all this activity and the essentially alteration to phyllosilicates and also the essentially degradation rates, which are extremely high back in this period here. And this brings us to the punchline here, which is the most significant questions are in understanding the geological, atmospheric, and biological history of Mars, using this inverse model and working backward, have to do with the Noachian period. How do we account for significantly higher erosion degradation rates and basically landscape planation? I mean, you're losing all kinds of craters less than 10 kilometers in diameter. It's a smooth surface. The craters, rim crests are gone. The craters are filled with material, et cetera. And then how do we account for the precipitous subsequent decline after the end of the Middle Noachian? And what processes formed the ubiquitous early Noachian phyllosilicate deposits? And how are these two issues related to the nature of the ambient climate and the atmosphere? And finally, of course, this is a paper that's submitted to astrobiology. We had an astrobiology paper on this at the Astrobiology 2025 meeting, and we were encouraged to submit this to a special issue of Astrobiology from that meeting. So that's the big question too. What are the astrobiological applications? You better be looking at Antarctic analogs here because we think it's really been cold. So this gets back to the question here. What is the influence of the three major impact basins? Hellas, defining the base of the Noachian, Isidis, and then Argyre in the middle Noachian. What's up with this period here where in fact we're before the valley networks and we're in the major part of the Noachian, okay, the vast majority of the Noachian. So what are the predicted effects of these big impact basin formation? So we've looked at this significantly. Ashley Palumbo, a student of mine at Brown, we published 4 or 5 papers on this. Martin Turbet at the LMD in Paris and others have worked on this problem, and following up on the work of Segura and Toon and others. And the key points here is the effects, the predicted effects based on the modeling, is that impact stripping of some or even all of the ambient atmosphere. Wait, what's up with this, right? I mean, you could be getting rid of a significant part of the atmosphere with each of these 3 events, let alone the previous ones. Maybe Mars' atmosphere is mostly a secondary atmosphere. Maybe the primary atmosphere has been stripped off. It also predicts excavation of subsurface crustal and perhaps mantle material. So we have a lot of ejecta coming out, and it's redistributed over the surface, significant parts of the surface, because these are huge basins, of course. And most importantly and interestingly is heating and mobilization of crustal material, including ground ice and groundwater, and incorporation of this into a transient atmosphere. This transient atmosphere rapidly and torrentially rains out as the situation cools subsequent to the event, and this causes widespread erosion and terrain leveling. And finally, it turns out that when you do the models here, this climate returns to pre-impact conditions within a relatively short geological period of time. So that's kind of interesting. Okay, so here's a model. Here's the model. Okay, basically summarized from follow-up work from Segura and Toon and these other authors here with Ashley and Martin Turbet. And so here we have the event. You get a silicate vapor plume formation. It expands and cools as it condenses and condenses out. Water vapor is then coming out of the atmosphere. It condenses and you get a global rainfall. And this induces an intense hydrological cycle. And that's all over in a few hundred years. So these are major events. And the implications are incredible because indeed, we call this the impact cratering atmosphere and surface effects model. Impact stripping, we went through these 5 things here, but the key point here, how would the basin-related events affect the average erosion rates? This torrential rains, their global torrential rains, would be several meters a year and involve about 400 meters global equivalent layer of resurfacing effects. And each basin would induce a spike of very high short-term landform degradation and planation. So what does that look like? Do we see any evidence for that? We see evidence for that all over the place. Here, we've taken about 30 semi-random late middle Noachian, early Noachian regions and studied them. And you find landscape stripping, erasure of features. You can see that the rim crests of these things are gone. There's a lot of erosion. You can see planation. You can see, for example, this crater material is going from the rim. Rim material is eroding down into here, and it's actually flowing out into here. And we see soil regolith saturation, producing extensive soil water flows across the surface and global and local smoothing of topography. And also you see crater infilling. You can see here various levels of crater infilling, and the crater wall rills that you see are generally continuously being formed from material flowing in from the rim. So we see this as not a rainfall process because the rainfall is highly unlikely to occur here based on a variety of different pieces of evidence, and more that the individual impact events are causing these effects. And you can see here, there's also lobate flows like this one right here, which is down in this area here. Lots of evidence for regional planation, et cetera. We're continuing an analysis of these 30 individual areas, and we'll be presenting that at LPSC. So what about the phyllosilicates? Well, impact basin-induced rainfall, what does that do? It's globally and homogeneously distributed at very high rates, 2 meters per year. This is similar to Earth's tropical rainforest, characterized by very high temperatures, 373 K, okay? So these high temperatures of impact-induced rainwater and snow, together with the pervasive penetration of heat into the regolith, these are sufficient to account for the phyllosilicate alteration from an experimental point of view and any other way you can look at it. And you'll see that the phyllosilicate distribution is not unrelated to these 3 basins. So we, again, would argue that the early middle Noachian terrain planation and phyllosilicate formation, the ICASE effects, the effects of the three major impact basins, Hellas, Issus, and Argyre, could readily account for the vast uh, planation and high erosion rates that quickly tail off into the late Noachian, early Hesperian. And we would conclude from this that Mars might have been, in fact, cold and icy throughout, punctuated by transient events at different scales, and the atmospheric pressure may have been always less than a bar, maybe even much less than a bar. So this paper, Astrobiology in Review, I'll send that around if when we get the reviews back, etc. If you're reviewing it now, please be nice, and we'll press on. Okay. So what is the bottom line is, what about astrobiology? Now you think, okay, look, this is pretty tough surface conditions, and indeed that's correct. But the key point here is that in the subsurface, as we see in Antarctica and elsewhere, you can get a very, very significant biota. And the interesting news about this is that it's also providing the nutrients which a biological community could thrive on. And these things will then be in the subsurface. They'll be released with the groundwater, like the eruptions from the Valley Network formation. No, I'm sorry, from the outflow channel formation. And in fact, any kind of impact crater will excavate there too. So we're thinking more like look for a troglodytic fauna. Troglodytic meaning, kind of deep down, hidden in the subsurface, and using other energy sources than we're used to with photosynthesis. So that's where we are today. It's an ongoing project. Stay tuned for LPSC. And really sorry not to be there, but I hope we could get some good input here to think about these implications of these big basins in the early to middle Noachian. Thanks a lot.
And
Stun
have
silence.
about 6 minutes for questions. Sorry, Bill?
Okay. So Jim, since you asked me questions about an hour ago, it's only fair that I give you questions back.
Yeah, we both gave 2 talks today, I think, right?
That's right, in different meetings, right? So, okay, so the question I have is this, is that there's a lot of other impacts other than the mega basins. And what's funny is that when I look at when we see evidence of direct water flow on Mars, it always seems to be happening when the impacts are sort of dying out. And there's not a lot of evidence for what's happening when there's still a lot of impacts taking place. So there's a mismatch there, and it's bothered me for years. Can you talk about that a little bit based on your ideas for this new model?
You mean the water seems to be unassociated with the impacts?
Yeah, you would expect that if water and impacts go together, that when you have lots of impacts, you should have lots of evidence for water because it's more than just the big basins. You have a lot of other impacts that are happening too.
That's very true. And I couldn't agree more. I think clearly the big basins are orders of magnitude different than the smaller ones, but each of these basins is going to have an effect. And it's a really big challenge. There have been a number of papers on this, which have tried to isolate what the key diameter is in terms of producing things that are more global in nature. So, however, later on, say for the model of the cold and icy highlands that I was showing, the mobilization of the top-down melting could, in fact, Karen Stakely has been doing a lot of really good work on this, and she has shown that maybe these intermediate peak ring basins and maybe even big uh, uh, complex craters could in fact be significant enough to create a spike, a climatic spike that could lead to a lot of melting on the surface. So it's a complex issue for sure, but the big basins are really, really, for example, the 373K from the torrential rainfalls is really, I think, the best explanation for the phyllosilicates. And you don't see we're going around now and looking at each basin and mapping out the distribution of the phyllosilicates and their ages and look for planation. That's what we're going to do with these 30 different areas here. And we already looked at that for the Isidis Basin, and there's very good evidence that there are features that are related to these major events. So, I think there are a lot of craters, which is good news for all of us here because it's job security. Sorting them out is going to require all of us together. And I see Clark Chapman in the background there. And Clark, I would just say that this is one of the explanations, if you will, for the loss of craters less than 10 kilometers in diameter early on. Okay, that is to say, this kind of planation here is a very, very good candidate for losing those, or the work that you and Ken Jones did early on, in which you noted that significantly.
I think Livio's hands is raised again, so go for it, Livio.
Hey, Olivia.
Hey Jim, nice to see you again.
Good to see you.
So, I was just having a thought. We have craters like Hale and Leo, which are pretty large and relatively well preserved, and both have documented evidence of what appears to be dewatering of the ejecta blanket.
Right.
I'm wondering if maybe part of the answer to the previous question is that it doesn't necessarily coincide with the impact, but follows the impacts.
Yeah, no, I think that's a very good point, Livio. And the two craters you mentioned are really important, and the latter one is very critical because you see radiating valley networks around that. They're very young. Stewart has done a super amount of work on looking at the ejecta and the secondary crater distribution center. But the point is, we had a paper in I don't know what it was, anyway, 2018 maybe, where we looked at the relationship of the ejecta and the valley networks, and indeed they appear to be coming out from underneath the ejecta. Okay, for the most part, they're not top down, and we found out with the size of the crater of Leo, et cetera, that it's more than likely that. Oh yeah, and there also was no evidence for any kind of rainfall or anything on top of that. Okay, so we concluded that in fact this was one of the periods in the Amazonian when the obliquity was approximately 45 degrees or maybe even 30 degrees, and that area was covered with snow and ice. And what Leo did was they excavated out hot ejecta, dumped it on the surface, and that was what created the energy source for the melting. I think the evidence is really good for that. And there are a number of places like that, and I like to call those false positives. People have said, oh, that must mean there was a warm and wet period and the atmosphere came back to the way it was in Anoakia.
Right.
But I would argue that they're false positives for that.
So I think maybe we could save the question for the discussion. It is in fact 2:45. So I think unfortunately we need to head out and on to our next speaker.
I appreciate that, and I'm sorry. Tonight in my family here, it's date night with my wife, and so I'm not going to be available. And I don't want to mess with
We
that.
ask the question while
Yeah.
we do transition.
Yeah, so how about Bill, you can ask the question now during the transition.
Okay,
and we'll
so-
keep doing two things simultaneously.
So the thing I was gonna ask is just related to the last question on Leo and the rest. I mean, my impression was some of these features would be more from hydrothermal systems made by the impact, not necessarily melting of surface, like ice or whatever. But I haven't looked at the geology. That was just sort of my impression. So how do hydrothermal, people ask the question, how do hydrothermal systems produced by the impact play a role in this?
I think they do, and I think a really good place to look for that is Gale, and maybe even Jezero. Okay, because that's up close and personal. I think there have been a number of really good papers about calculating out the decay time of the thermal input from that. And, I think Livio and Oz can talk to that too, in terms of the kinds of things they see in hot, in the Canadian Arctic craters. So it's a very good point. I think, the data we have from Gale crater, I think can be used to make some advances there. Okay. In the paper I mentioned in astrobiology, I spent a month or so going into the Gale crater data, but there's so much of it and it's so complex, and every outcrop is named something different that it's really hard to integrate, but I'm working on that. And I think it's going to help us to address that question too.
All right, so if we would like to thank Jim again.
Thank you.